Hi, so this is Deepak and I'm with Dhruv and Arshia. So today we are here to present our FoodVision AI project. So this is a computer vision project. The main idea behind this project is to see like how much calorie is present in food. So the user uploads the image of the food. The model is able to detect what food is it, and then the model is able to tell how many calories is present in the standard sizes of that food. So going right into the demo. So first we have the problem definition. So why did we create the application in the first place itself? So now people are becoming more health conscious. They want to know like how much calories is present in the things they eat, and they want to keep track of how many calories are they taking on a daily basis. But so often they don't have options to, like in packaged foods they know like how much calories present in the packaged foods, but the food you get in the restaurant or the one you cook in home, it's really hard to track how much calories is present there. So via our application what we want is we want the user to identify the food, be able to identify the food and the calorie present in them. So that's the main problem definition. Now what solution we did? So up to now it's our web-based application where the user just uploads the photos from their meals, and then our system uses a deep layer convolution neural network which is able to recognize food from 101 different classes, and based on those classes, after recognizing what food is it, it's able to tell how much calories is present in that. So as I said earlier, the target user is health conscious individuals whose number is like growing every day, people with dietary goals who want to limit their calorie restrictions on a particular day, and users with dietary restrictions, it comes on our future plan, but for now it's just calories, and then fitness enthusiasts. Now talking about dataset items, Harsha is going to go over it.
Yeah. So first of all, about the data set is Food 101. I say why it's called that way. There are about 101,000 images with 101 food categories. So it would be like 1,000 images per class, and the name comes from that. This data set is basically a wide range of different cuisines like pizza, sushi, burgers, and it is from Kaggle. So, the next slide, which is also mine. So, it makes sense that each image in this data set is labeled with exactly one of the classes, one of the categories. So it gives us, like, it takes us to the ground truth for the supervised learning, and then it takes us to the two-stage strategy, which is about the splitting of 70% training and then 30% test. And the 70% training is again 20% of it is validation, 80% for the actual training. So in a way, there's like 56% for training, 14% for validation, 30% for testing.
Okay, so now previous work and approach. So identifying food with computer vision is not a new thing. A lot of work has already been done in this sector by different players as well as individuals. So the Food 101 dataset was first introduced in 2014, and what it did was it used traditional computer vision features and classical machine learning models to achieve often around 50% accuracy. Then came the deep learning methods with deep residual network. It became the deep residual network became like standard for image classification. Architectures like ResNet used skip connections to verify deep network without the usual vanishing gradient problem, and it achieved a very strong performance on the large scale datasets. So even for our project, we are using ResNet 50 based architecture. We leverage transfer learning from the ImageNet, and then we use it to classify the Food 101 dataset images, different things. Talking about the technical design, we use ResNet 50 convolutional layers as our base model, and then we freeze like early 145 layers and the rest of the 30 layers. So ResNet has like 175 layers. So we freeze the initial 145 and then we fine tune the other 30 layers, and then we added our own dense layers, which is like with the ReLU activation functions, the first dense layer was with 256 neurons, the second with 128, both with ReLU, and our third layer was our output layer with the softmax function for the classification of multi-class thing. Then coming to the training configuration, it's gonna be like, how do we train the model? So first we need to pre-process the input. So we convert the input images size into 224 into 224 resolution. This is our learning rate, which is also known as Adams optimizer. So what it does is, based on the gradient, it helps to optimize the weight so that the model is accurately able to classify the images. Batch size is 32. So at the moment the model only takes 32 images to train, and early stop patience is 3, which means that if validation accuracy doesn't increase up to 3 epoch, we stop the training. So coming to the data augmentation is so it's a method to just train the model more effectively. So we do rotations, like, so that the model can, even if the image is presented in different way, the model is able to recognize what is it. So it's just a method to increase the robustness. So we rotate, we shift the width, we zoom in, we flip the images, we resize the same images to train the model to be more robust. Then we have the backend architecture, which Dhruv is going to be speaking about.
Now I'll talk through the backend architecture that connects the model to the web app. So we implemented the backend in Flask, which is responsible for receiving the image from the front end. Then it applies the pre-processing pipeline. It runs through the training model for inference. Then it maps the predicted class to the food name and its nutrition value. Then it returns a JSON response with label, confidence, and calories. To talk about the pre-processing steps, it receives an uploaded image file, then it resizes it to 224 by 224 pixels, converts it into a NumPy array, and adds a batch dimension. Then we apply a ResNet 50 pre-processing function, which includes like mean subtraction for each channel. And then we call like model.predict on this process tensor, which decodes the predicted class and formats the response as JSON. For next thing, nutritional database, uh, we built a custom nutritional database that covers all the 101 categories. For each class, we store calories per 100 gram, additional metadata as needed for estimation. So the database structure is like based on portion sizes, small, medium, and large. The calorie estimation pipeline is something like when you take a predicted food class from the model, it looks up it looks up the calories per 100 grams in database, and then it assigns a gram amounts to small, medium, and large portions, and then it multiplies and gets you a estimate calorie on the front end.
Okay, so the front end is basically React with white, and there are some specific goals that we were intending for. First of all, the clean interface, which would be like an intuitive page. Users can see clearly everything, and then they can upload their meal photos. There's like the drag and drop support. So basically, users can just drag an image to the drop zone, or they can also click to select a file like locally. Then there will be a prediction. As soon as the backend responds, there will be a predicted food label. There will be the confidence indicator in terms of percentage. There will also be a portion selector, just a very simple, small, medium, large, and then the calorie would change accordingly. This is the only thing that the user has to do. Like they need to upload a photo, adjust the portion size, and before they adjust anything, the portion size one is chosen by default anyway. And so the layout adapts to different screen sizes, so you can also use it on laptop or smaller devices.
Alright, so now confidence visualization. Since we have less time, almost 5 minutes, I'll quickly go through the slides. So confidence visualization is like Since the softmax function gave us the probability like between 0 to 1 regarding which class the data belongs to, so we also saw that confidence in our front end as well, which we'll demonstrate later on. And based on it will show like, so it says like how much the model is confident about its prediction. So if it's 100% or more than 90%, we can say like model is, we are sure that this is the required food. And so that's the confidence visualization. And for our result and evaluation, what we found was, in while training the model for 101 classes, our validation accuracy was 58%, which was pretty good for 101 classes. And then as we decreased the classes, for 71 classes it was like 67%, but we went on with the model that gave us 58% validation accuracy, but with large number of classes. But even with 58% validation accuracy, what we found was during the testing, it almost more than 90%, 95% of food it was able to identify it correctly with high confidence rate. So it says like even if the validation accuracy is less, in the real world application it was doing good. And we had 101 classes, and inference time was less than 1 second, which meant that model was able to produce result within less than 1 second time. And key technical
Just to go
challenges,
over
yeah,
through the
just
like
Dhruv
key
will go over
technical
this quickly.
challenges, let me go through them quickly. We faced like the computational challenge. Training on 101,000 images was like a huge computational resources task, and it took a huge training time. Next was noisy and diverse images. So images were like varied in lighting, background, and composition. So we needed strong data augmentation to generalize. And then next was consistency between training and deployment. Every step in the pre-processing pipeline needed to match between training and inference. For the lesson learned, we learned that there should be a pre-processing consistency, transfer learning in which the using like pre-trained models, like which significantly reduces the data and training time required for providing strong performance, data augmentation, model design, and a configuration of backend services with the front end and the inference.
Alright, so now we'll go to the demonstration. So right now this is our local code repo. So we have backend, front end. In the backend we have .h5 file, which is our model file. Now to run this, what we need to do is, the first thing is we need to run the backend. So python app.py, if we do it, we will, our backend will start to run. So it starts to run. And for the front end, what we need to do is go to the front end, change the directory to the front end, and do npm run dev. After we do this, our local host will get a URL, and when we click the URL, it opens. This is our front end thing, and our backend has already started to run in the another terminal. So our backend has started to run, which uses the model to predict the food classification. So now let's click and drop the images here. So suppose I drop this image. These are mussels. So mussels, when it do identify food, within 1 second it says like it has 344 calories, and it also says like based on the portion size. First it says like 100% confidence, so it identified the images pretty accurately. And then it says like based on the servings, how much calorie does it have. So 516 calories in the large serving, for medium it's this, and for small it's this. Now suppose we take another image. So let's take this one. This is an omelette. So we take omelette. For omelette it says like, it says 71% confidence, also because the image is like this, so it's a confusing thing. So for small it says for 2 egg omelette it's 154 calories, for 3 egg it's 231, and for 4 egg is 346. So based on the food it will give you the portion size. So for omelette it's 2 egg, for and for other thing it's other, and it will say like how much calories present there. Also let's do for ice cream. We see for ice cream it says like how many scoops, how many calories are present over there. So that's the ice cream thing. Now just to give you a demo, let's take one thing from there. So suppose we have here falafel, and if I go and search falafel in the internet, so we have here falafels. And if I save this image as f7 in the desktop, if I go to the front end, upload the image, and then do identify food. So it's able to recognize falafel as 99.9%, and for here it says like for small portion, which is 2 to 3 balls, the calorie is 199, for medium 399, and for large 599. So this is how model works. It's pretty accurate in identifying most of the food. To give the another example, maybe we go and do, suppose, pancakes. And so this is the pancakes. I'll download this image as P2. We do this, and let's do this. So front end P2, and we identify pretty quickly. So for small 2 pancakes, how many we have, for medium how many, and for large how many we have calories. So yeah, this is how our model works, and this is our front end and back end is working. So now that's the end of the time, so I'm just gonna stop the recording. And yeah, this is our computer vision project. Thank you so much for joining in, and let me stop the recording.